Hi friends, we shall try to understand the concept of system of coplanar non-concurrent forces. So here the first thing is very important, that the forces must be coplanar. So all these forces must have their line of action in a single plane. So let me show you a very simple example, friends. Suppose we have a body like this. So we have got a body which is in the form of lamina. On this particular plane we have got a force like this. So this is the first force acting over here, and let's say we have got another force, and we have got third force acting like this, let's say. So we have got three forces, you can see here. Let's say this force is F1, this force is F2, and this force is F3. So there are three forces acting in this particular plane of the body, right? So these three forces are the coplanar forces. So we can directly write down that forces F1, F2 and F3 are coplanar forces. They are coplanar forces because they are acting in the same plane. Now what I'll do, I'll extend their line of action and let's see what happens. So let's extend the line of action of each force. So let me first extend the line of action of force F1. We'll also extend the line of action of F2. So we have extended the line of action of force F2, and let's also extend the line of action of force F3. So if you see like this, F1 and F2, they are intersecting at this particular point, friends. Okay, let me call this point as point A. While force F3 and F2 are intersecting at this particular point, let me call point B. And force F3 and F1 are intersecting at this particular point at point C. So there are 3 points of intersection, you can see. So all three forces are not intersecting at a single point, but they are intersecting at three different points, as you can see here. So there is no common intersection point of these three forces. Okay, since forces F1, F2 and F3 are not intersecting at same common point, we call them as non-concurrent forces. These forces are in the same plane, so they are the coplanar forces, that is fine, but they are not intersecting at the same point. Therefore they are called as non-concurrent forces. This is the simple point of identification about coplanar non-concurrent forces. Now what is significant of this coplanar non-concurrent forces? Please remember, so whenever we have a system of non-concurrent coplanar forces, there will be what? So there will be a resultant force of this particular system of forces. Okay, so what we can do? We can represent the entire system by a single force. Okay, so we can represent the number of forces, okay, by a single force, which will be called as resultant force. So we can say that we are going to have a single resultant force. This may be called as the resultant force, that is Fr, resultant of all these forces. Okay, so the system will have the resultant force that you may be calling as Fr. Okay, and one more thing, since it is system of non-concurrent forces, there will also be a resultant moment. There shall be a resultant moment of forces. Okay, and that you can represent by Mr. So there will be one, so system will have one resultant moment of forces, that is I will be calling as Mr. Is that okay? Mr. So it means the entire system of forces can be represented by a single resultant force and by a single moment of force, that is Mr. That is very important. So I'll write down note here. The given system of forces can be represented by a resultant force Fr and a resultant moment Mr. So this is a very important point, friends, that you can represent the given system of the forces, this system of forces, just by a resultant force Fr and a resultant moment Mr. Okay, so let's see one example of a system of coplanar non-concurrent forces. So friends, let's solve a problem based on system of coplanar non-concurrent force. So let me read the question first. A 2 by 4 meter plate is subjected to a system of 3 coplanar forces as shown in the figure. Determine the resultant force as well as its location with respect to point O. So they have given us three forces. The one force is this, which is 3 kilonewton and which is acting at angle 60 degrees. The another force is this one, which is acting vertically upward and having value 4 kilonewton. Okay, and the third force is a force of 6 kilonewton, which is acting at angle 45 degree with the horizontal, we can say. So we have got three forces acting on this particular plate, which is having dimension 2 meter by 4 meter. Okay, now here we have to find the resultant force as well as its location with respect to point O. So here we have got point O, friends, and we need to find out the location of the resultant force with respect to point O. Now let me remind you again, this is a system of coplanar non-concurrent forces, because if I extend this force, friends, and if I extend these two forces, okay, so they are not going to cut at the same point. They'll be cutting at different points. So this force and this force will intersect somewhere, and these two forces are intersecting here, and this force and this force will intersect somewhere over here, okay. So they are not going to pass through a single common point. So it is a system of coplanar but not concurrent forces. They are not passing through the same point, okay friends. So now, so we know that when we have a system of coplanar non-concurrent forces, there will be a resultant force as well as there will be resultant moment. So what we will do, we'll first find out the resultant force of this system of forces, and then we will find out the resultant moment of these forces about point O. And from these two informations, we can find out the distance of resultant force with respect to point O. So let's first calculate the resultant force. So as we know that in order to calculate the resultant forces, so we have to resolve each force along x and y direction, friends. So let me call this is the x direction and the vertical one is the y direction. This one is the y direction, let's say. This is the x direction, this is y direction. So I'm going to resolve each force along x and y direction, and I'm going to find out its x component, that is fx, and I'm going to find out its y component, that is fy. Now we have got force 3 kilonewton. So this is going to be 3 kilonewton, friends, here. Then the another force is 4 kilonewton, and third one is the 6 kilonewton force. Now I'm going to resolve this particular force, which is 3 kilonewton, in x and y direction. So we can resolve this force 3 kilonewton along x direction, which is going to be like this, friends. And this value will be called as 3, and the angle is here, so it is going to be 3 cos 60 degrees. Okay. And similarly, I can resolve in the y direction, which is this way, and this will be what? 3 sin 60, because the angle is made along the x direction, so it is cos, and angle is not made along the y direction, so it is sin. So 3 sin 60 and 3 cos 60. Now this particular is only in the vertical direction, so I don't have to resolve in the x direction, because x direction the component is going to be 0. So we have only y component for this particular force, that is 4 kilonewton. And here again 6 kilonewton we can resolve along x direction like this. So it is going to be 6 cos 45 degrees, and I can also resolve along y direction like this. This is going to be 6 sin 45 degree, friends. Okay. So we are able to resolve all three forces along x and y directions. So let me write down the values. So 3 kilonewton. So it is again towards right. So towards right we take positive, this is positive, and this upward we take positive, friends. Towards left we take negative, and downward we take negative. That is sign convention we follow generally. So this is 3 cos 60 is towards right, so positive, friends. Positive 3 cos 60. 3 cos 60. And similarly this one is upward, so it is positive. So plus 3 sin 60. Now let's talk about this particular force, 4 kilonewton. So it has no x component. So x component is going to be 0. It has only y component. Y component is simply 4 kilonewtons. Now we'll talk about this 6 kilonewton force. So along x, again positive direction. So 6 cos 45, and this is again positive, that is 6 sin 45. Okay. So we have resolved each force along x and y direction. Now we'll find out the summation of fx and summation of fy, that is the addition of these values. So here we'll get summation of fx, friends, and if you add this you'll get summation of fy. So if you do that, the value would come as, so if you do this, if you add these values, you'll be getting summation of fx as 5.741, that is kilonewton. Okay. Similarly, if you add these values, the value of summation of fy you'll be getting as 6.841, okay, kilonewton here. So like this you can find out the summation of fx and summation of fy. Now the resultant force, let me call fr, is given by square root of summation of fx square plus summation of fy square. So if you substitute the values of summation of fx from here and summation of fy from here, you will get resultant force will be 5.741 square plus 6.841 square. So if you simplify this, you'll be getting the value of resultant force as 8.930 kilonewton. So now here we got the value of resultant force of these three forces. Okay, that is this one 3 kilonewton, 4 kilonewton and 6 kilonewton. They are going to collectively give you a resultant force equal to 8.930 kilonewton. Now this is about the magnitude of resultant force. So we have got the resultant of this system of forces as
8.930 kilonewton. Now we have to find direction of the resultant force. So direction is given by theta. We can say it is the angle at which the resultant force is inclined to the horizontal. Okay. So it is nothing but tan inverse of summation of Fy divided by summation of Fx. Okay. So if you simplify this, you will be getting tan inverse of summation of Fy we have got here 6.841 and that divided by summation of Fx which is 5.741. So now if you simplify this angle theta is going to be approximately 50 degrees. So if you look at here, this is the angle at which the resultant force is inclined to the horizontal. Okay, and the next, the value of resultant force is given as 8.930 kilonewton. So we got the magnitude as well as direction of the resultant force. Okay, now there is one more thing I would like to find, that is resultant moment. So let's also find out the resultant moment. So about point O. So let's say the moment of forces about point O, because we have to find distance of force from with respect to point O. So we'll first find out the resultant moment what is going to act on is. Okay, so the resultant moment, or we can say the moment of all the forces about point O, which is called as resultant moment, that is Mr. So let's do that, friends. So now if you see here, now we'll take the components, friends. So the 6 cos 45 is passing like this. Okay, so this particular component is acting along this line. So distance of this particular line from this particular point O, if you look at here point O, is 1 meter. So this is going to rotate the plate in the anti-clockwise sense, and I'm going to take anti-clockwise as negative. Okay, so 6 cos 45 into 1, that is minus 6 cos 45, and then the distance from point O, the perpendicular distance is this distance, and it is 1 meter. So into 1 meter, because it is rotating plate in the anti-clockwise direction, so I'm taking it as negative. Okay, so anti-clockwise I'm taking as negative, and the clockwise I'm taking positive. Now next, this particular component, that is 6 sin 45, is again going to cause the anti-clockwise rotation about this particular point, and its distance from point O is 2 meters. So again minus 6 sin 45 into the distance is this distance, friends, that is 2 meters. Okay, so we got the moment caused by these two components. Now let's talk about this 4 kilonewton. The same thing, it is going to act along this line and it is going to rotate beam in the anti-clockwise direction, right, like this. So 4 kilonewton times this distance, that is 2. So again minus 4 into 2. So this particular force is also completed. So moment due to this particular force also we got. Now remaining is this force, that is 3 cos 6. It is going to rotate beam in this particular direction, that is the clockwise sense. So this is going to be positive, friends. Okay, so 3 cos 60 and the distance from this particular point O is 1 meter. This I'll be writing plus 3 cos 60 into this distance, friend, that is plus 3 cos 60 into this distance, which is 1 meter. So 3 cos 60 into 1. Okay, and it is positive because the rotation is this particular force 3 sin 60 will also rotate the plate in the clockwise direction, that is also positive, is going to come here. So now this is going to be 3 sin 60 into this distance, is 2. So 3 sin 60 into 2. Okay, so now all the forces has been taken care of. So the moment due to all these forces is this particular value. So if I simplify this, you'll be getting the resultant moment. Okay, about the resultant moment about point O. I'm taking with respect to point O, friends. So let me solve this. So if you simplify this, friends, the value of Mr is going to come as, so if I simplify, so the value of Mr you will be getting as minus 14.03 kilonewton meters. Okay, so friend, this minus sign indicates that your due to application of these forces, your plate is going to rotate in the anti-clockwise sense. Okay, it is going to rotate like this. Okay, so negative sign indicates the rotation of plate is going to be in anti-clockwise direction. Okay, that's fine. Now we know that this is the value of what we got, resultant moment, and we got resultant force. Okay, and the angle of, we also got the direction of what you call direction of the resultant force, which is theta. So let me take one more. Now here if you look at, friends, now here if you look at, this is the resultant force, that is 8.93 kilonewton, and this is the resultant moment about point O, right? So now we know that the resultant force we must have the same moment equal to this. Okay, so by that rule I can say that if your force is acting at distance, let's say d, so resultant force into some distance d must be equal to what? Resultant moment. So from here you'll get d as resultant moment with respect to point O, let's say, because we have found the resultant moment with respect to point O, and that divided by the resultant force. Okay, so this particular expression will give you the value of the distance of resultant force with respect to point O. If I simplify this, okay, so from this particular expression we can say that the distance is nothing but the resultant moment divided by the resultant force, and that value, let me put it here. So it is, the resultant moment is minus 14.03 and resultant force is nothing but 8.930 kilonewton. So 8.930. So if you simplify this, friends, you'll be getting the value as minus 1.571. Now meter, it will be in meters because distance we have taken in meters. Okay, now you have to understand how to interpret this. Okay, that is very important over here. Now since it is giving negative resultant moment with respect to point O, so we can say that you should apply the force F such that it should rotate the beam in the anti-clockwise sense. So suppose if I apply force over here, so suppose if I apply force over here, let's say like this. Okay, its angle is, this angle is given as 50 degrees. So in first quadrant, friends, because summation of fx and summation of fy both are positive, so it is going to be first quadrant like this. We have quadrant system this way. So since your force is at 50 degree in the first quadrant, it will be like this, friends. Okay, this is going to be angle 50 degrees. Okay, so that's what I'm telling you. This is the resultant force which is acting at angle 50 degree with the x direction. Okay, so it means here, so if I apply force in this way, friends, what is going to happen? Your beam is going to rotate in the clockwise sense due to application of this force. Okay, so if, so that is positive, we can say. Okay, but sorry, your plate is, this plate is rotating in the anti-clockwise sense, which is like this. Okay, so we have got, see, the moment, negative moment. So negative moment means what? Anti-clockwise. We have taken clockwise positive and anti-clockwise negative. So this indicates what? Anti-clockwise rotation of the plate. Okay, so it means if I apply force like this, it is not going to rotate in the anti-clockwise direction. Okay, so it means you have to apply force somewhere like this. So if I apply force like this at this 50 degree, somewhere here, let's say Fr, and this 50 degree, friends, so you will see that due to application of this particular direction of force like this, okay, your beam is going to rotate in the anti-clockwise sense in this direction. So this is the correct way of understanding. So just I'll draw one small circle here just to illustrate what is the meaning of location of resultant force. Fine. So it means now I would like to apply the resultant force. So resultant force is going to act somewhere here, let's say at this particular distance, and this is going to be resultant force like this, friends, Fr, and its angle with respect to the horizontal, this angle which what you have calculated, right, this angle is nothing but 50 degrees, 50 degrees, and it is going to rotate the plate in the anti-clockwise sense in this way, right? This is Fr. This distance from here to here, which is d, we can call. So d we have already got. This is the value of d, friends. Okay, so this is the value of d. D is the distance from point O. Here the point O is here, friends. So from point O to the point of application of the force is called as d. This distance we got as d. Okay, so we are referring to the perpendicular distance of the force with respect to point O. Moment caused by this resultant force must be equal to the overall moment of forces about point O. So if you want to find the distance of force, you divide the resultant moment with the resultant force, you will get distance. Okay, and by considering the sign convention, that is clockwise or anti-clockwise, you can locate the exact point at which the resultant force is going to act. Thank you very much.